All right, so in this lesson, we're actually going to be coming back to solids of revolution. So again, that's a two-dimensional region created by the intersection of different equations that's revolved around either a horizontal or vertical line. How we're going to be studying this different today is rather than calculating the volume using discs or washers, is we're going to find or use a new method for calculating these volume called shells. And the purpose of learning a new method for calculating these volumes is they're oftentimes just due to the nature of the curves that you're using for the area that you're evolving, might get kind of messy for the setup, or might actually not be able to be written using disk method or calculated using disk method. So this would just be an alternative to that. So just to get started, we'll talk about a little bit what do we mean by shells. So we're actually using something similar to the disk and washer method. We're still going to be using cylinders, but we're going to be using the lateral surface area part of the cylinder. Or if you think of a cylinder as like a soup can, like the label of the soup can part of this. So that's what a cylindrical shell will be. How we think of creating these three-dimensional solids can be think of the idea of a tree growing. I know that maybe sounds kind of silly, but when a sapling starts out really tiny and it grows into this big tree, the trunk is increasing, the diameter is increasing, the radius is increasing as the tree grows. That's actually how we calculate using the shell method. We think of something starting around the line that we're revolving around and growing out from there. Another way to think about this is if you can think of like a piece of candy being dipped and layers being added onto it, kind of like a gobstopper. So we keep adding a layer of shell each time, or like kind of something like a candle being dipped and having layers added to it. So each time a layer is added, the volume gets larger. You keep adding another shell. So if we look at this area right here, that's bounded by the x and y axis, and it looks like a parabola in a vertical line. If this were revolved around the y axis, the other half of the solid would be over here. We've practiced looking at these volumes and calculating their volumes using disks, but I have just a quick little animation that just shows where crudely where the shells are coming from. So these shells are kind of large, but if you want to just check out how this application is going, if you want to take a look here, you can see the different shells being added each time. So, and you can see that they're growing around the axis of revolution. So similar to what we've been doing in the last couple of lessons, we want to look at two-dimensionally what the shape is, our cross section, or like when we chopped up the volume with disks. Well, we're going to be, we want to add up an infinite number of these shells. So when we want to base our formula that we're going to be using for integration on the surface area of a cylinder, but we only want the lateral part of it. So we only want like the label on the soup can. So what's the formula for that? I know that the length, or that's a rectangle, so it's going to be base times height. But it's not just any base, it's the base that would fit around this circle. And the length that goes around the outside of a circle is the circumference of the circle, which is 2 pi radius. And then we still have the height of that rectangle. We can still just call that height. So that's the surface area, or the lateral surface area of the cylinder. So that's going to be what we refer to as a shell. So the volume formula that we're going to be integrating is going to take on that same form. So we're going to have a 2 pi coming from the circumference part of that formula, and then multiplied, I have the shell radius times the shell height. So there's the R and there's the H. And then depending on what we're revolving around, it's either going to be a dx or a dy problem. Being a visual person, I like to draw in a shell and I try to picture what the thickness of that shell is. And if that thickness is an x thickness, it's a dx problem. If it's a y thickness, it's a dy problem. Some people prefer to think of it this way, that when we integrate, it's going to be perpendicular to the axis or direction of rotation. So for instance, if we revolve around the y-axis, which is a vertical line, then it would be a dx problem. But how you choose to think about that would be up to you. Again, whether or not, because some people have trouble visualizing the thickness of a shell. Also, the variable for this would be the opposite of what it would be for disks. So if it had been a dx problem for disks, when we calculate the volume using shells, it'll be a dy problem. Oops. Alright, so let's find the volume formed by the region 4 minus x squared, y equals 0, and the y-axis revolved around the y-axis. So here's the region that we'll be revolving, and we're revolving it around the y-axis. So the other half is going to be over here. So this will be kind of almost a little bit of a bullet-shaped kind of solid. So what I want to do first before we actually get into setting up the integral is to actually just draw in a few shells. So remember that the shells are going to be growing from the axis of revolution, so the line that we're revolving around. So one of the shells that's really close to the y-axis here. Alright. So they're going to be really skinny shells up there that are tall. And then as we move throughout the region, if we're out here, here's what one of the shells would look like. So so shorter, but a larger radius. And then way out at the ends of the region, as we get farther away from the axis of revolution, the radius of these shells is quite large and the height is quite short. So just to draw in on this one here, so here's where the radius would be, so that's a representative r, and then that would be the height of the shell radius. So let's actually come up with the integral for what this would look like. So one of the things that we need to practice doing is identifying the shell radius and the shell height. So that's going to probably be the most challenging part of this process for you, just because you're using a formula that was similar to disks, but the way that we identify these is different. So again, the setup that we're going to be using is 2 pi RH. So we need to identify that radius and that height. So I've drawn in a representative shell here already, so you can see the cylinder part of that. So this would be the R and this would be the H. What may be helpful is to identify this ordered pair that's right here. So again, I am on the parabola 4 minus x squared, so this ordered pair is x and then 4 minus x squared. So my radius of this shell is going to be x, and the height is going to be coming from the height that's on the parabola, so that's going to be 4 minus x squared. If I am deciding whether or not that this is a dy or dx problem, I try to visualize the thickness of this shell. So you can think of the shell like it's thin like a piece of paper. It's actually thinner than that, but the thickness of this shell is an x thickness, so this is a dx problem. So the x lower bound for this region is 0. This parabola intersects the x-axis, and you could find this algebraically or use your calculator, but it does intersect at 2, so from 0 to 2. And then it's going to be the radius, which is x, multiplied by the height, which is 4 minus x squared dx. And then in this lesson, we'll just put the setups. If you do need to get the volume by hand, or if you do actually want to calculate the volume, you can certainly just use technology to integrate that for you. All right, so let's go ahead and look at another, try to do a setup for another volume. So it says find the volume of the solid of revolution formed by revolving the region bounded by x minus x cubed and the x-axis in the first quadrant about the y-axis. All right, so then here's what it would look like more in a standard viewing window. We want to zoom in on the part that's in the first quadrant, so checking this out here. This one of the zeros here is 1, so that length there is 1. So when we revolve that around the y-axis, there will be a symmetrical portion over there. And I would recommend drawing in a representative shell that may help you to more easily identify the shell radius and height. Since I'm revolving around a vertical line or the y-axis, that this is a dx problem, the thickness of each shell is an x thickness. Here's the radius and here's the height. The radius here, that's going to be changing throughout the region, and that length is x. The height is coming from the cubic x minus x cubed. So if I want to go ahead and set up my integral, I'm going to have 2 pi. Lower bound of this region is 0, upper bound is 1. The radius is x, and the height is x minus x cubed dx. So you may be thinking to yourself, is the radius always going to be x or y? Well, not necessarily. It depends on what you're revolving around. So for instance, let's look at something else. So find the volume formed by the cubic y equals x cubed plus x plus 1. So pictured right there, the line y equals 1, the line x equals 1, revolved around the line x equals 2. So let's go ahead and get our sketch drawn in so we can identify the radius and the height. So here's the line y equals 1. It's going to go this way. And here's the line x equals 1, so it goes there. So here's the region that we're going to be revolving. Okay, here's the line x equals 2, so that's right here. So if we're revolving around that line, the other if we want to draw in the other part of the solid, it'll be, over here. Just try to maybe make a symmetrical 2D representation. So if we wanted to color that in a little bit, because drawing in that other half of it would help you to sketch in a shell. So let's go ahead and sketch in a shell. You just pick a point in the region. Sometimes I like to put one kind of in the middle so I can see it clearly. But the other half of the shell would be over here. So there's a representative shell. So I would again recommend drawing in to help you identify the radius. So there's r, and there's h. So we want to determine, what is the length of this radius? So anytime that you're not using the x or y axis, and let's say that you're bounded by 2 equations, you want to continue to use those same rules that we talked about when we did area between curves. Since my radius goes from the line x equals 2 over to here, I want to do right curve minus left curve. So this length here is x, and this whole length here is 2, so that makes r equal to 2 minus x. So right curve minus left curve. Okay. When we go ahead and we find the height is going to be from the cubic down to the line y equals 1. So top curve minus bottom curve. So the cubic x cubed plus x plus 1 minus 1. Okay, which simplifies to x cubed plus x is my height. Okay, so I go ahead and I'm going to have 2 pi. I'm revolving around a vertical line. The thickness of the shell is an x thickness, so my lower x bound is 0. My upper x bound is 1. The radius is going to be the 2 minus x. and the height is going to end up to be x cubed plus x, because remember it was plus 1 minus 1, and then dx. So in this lesson, we came back to looking at solids of revolution. We just have an alternative way to calculate the volume by using something called the shell method. The shell method is similar to the disk method in the fact that they both use cylinders, but the shell method uses this lateral surface area of a cylinder formula to create the volume versus the volume formula for the cylinder. And you're using the opposite variable that you would have if it were a disk problem.